directions that they don't know of. And they cannot visualize and they cannot imagine because they've never seen them before and they've never bothered to even think about it. So the only way to get them to understand this, well, the easiest way would be to lift them up and show them their world from above, and they'd be able to see inside of everything. And they would be really weird. But 3 dimensions, they'd notice that in 3-dimensional world, instead of having a 1-dimensional field of view, they'd have a 2-dimensional field of view, and you can see so much more that way. But if you're not allowed to show them, lift them up and show them this 3-dimensional world, another way is to use an analogy. So you could tell them about a 1-dimensional universe and use that similar story, tell them about how they would show that to 2-dimensional. Now imagine that I want to tell you about 4-dimensional. I've used this story, which sounds silly and pointless at first, but it actually does have a point. Just as you can go from 2 to 3, you can go to 3 to 4. The thing is, there's no limit on dimensions. So, like, we have this built-in sense that 3 is a limit, but it isn't. There could be a 4th. Just as those flatlanders, they would think their whole lives, they'd always think that 2 was a limit. They'd think that, they really would. They would think that there was something special about 2-ness, 2 dimensions. But there wouldn't be. That's just because their universe just happens to be 2-dimensional. That's just the way they happen to be. Just like we happen to live in the Milky Way galaxy. It's not a special galaxy, we just happen to live in it. Similarly, 3 dimensions is not special. We just happen to live in 3 dimensions. There's no mathematical limit on them. In fact, there's simulations of 4 dimensions. And let me show you a little simulation here. So this is 4D toys. So I'll explain this more in depth later. But here I'm scrolling through cross sections of a 4-dimensional object. There are 3D cross sections. So maybe I should get back to the presentation plan. Alright, so okay, so first we've got to make this clear what the 4th dimension is. I'm not looking at time. Time is a dimension, but it's different than space. How? Well, I can move forward and backward in space. I can move in space however I want, but I can only move forward in time at a very fixed velocity. With general relativity, they kind of bend a little bit, but for the most part in everyday life, space is always constant and time is always constant, and the effects of relativity are so unnoticeable. And even with relativity, there's a huge difference between space and time. Time is how things change. Things change through time, but space is the stage in which things move around. So this 4th dimension of space would be like any other. You'd be able to have it interchangeable, so it wouldn't be any different than this way, or this way. And it would not be smell, so one thing that really bugs me is when you go to a theater or something and it says this is a 4D movie. It's not a 4D movie. Just because it has sensations or smell, it's not a dimension. Now, if I made this video game, right, and it was a completely flat video game, all 2 dimensions, and I, included this, the little device you could buy for it that, gave you smells for the game, I don't know, go to the forest, you can smell the forest or whatever, and I called it a 3D game, people would be all excited, and then they get it, and they discover it's the 2D, the most flat game they've ever seen, and they'd be angry at me for telling me it's 3D, because it's clearly a 2-dimensional game, and I'm like, oh, but the smell's the 3rd dimension. That's not a dimension, that's a smell, it's something different. That you can't move around in that. Similarly, if somebody tells me there's a 4D movie going on, and I go inside, and it's just 3D with a bunch of smell, I'll be like, well, that's disappointing. I was expecting something actually 4D. Alright, 4D. Why do we bother? Alright, so trying to visualize 4D. I've been trying to visualize for many years. I feel like I've gotten pretty close sometimes, but I've never quite got it. I've read a couple of people's posts, a couple people on the internet said they've managed to, visualize it, but it's really hard and really elusive. So, yeah, 4D is tricky. Alright, so one way to understand 4D is to use cross-sections. Now, first, I'm going to just get to the elephant in the room here. Why don't I show you? Why don't I just show you a picture of the 4-dimensional stuff? Because you cannot draw it on a piece of paper, and you cannot show a picture of it, and you cannot imagine it without expanding your mind's eye. Because the problem with it is that, remember, 3-dimensional stuff you can see from a 2-dimensional view. 4-dimensional stuff you need a 3D view. So not a view like this, a view like this that you can see all points of as if you're looking at looking at it on a sheet. Okay, so that's kind of hard to understand. So why don't we start with something simpler? So drawing a 4-dimensional thing on a 2-dimensional surface, can't do. Okay, help understand that. What about drawing a 3-dimensional object on a 1-dimensional surface? So if I give you a single line of pixels, and I tell you to draw a cube or a beach or like something, like anything that's 3-dimensional, that's clearly 3-dimensional, I ask you to draw it on the single line. 1-dimensional, you can't do it. You can like draw a cross section of it, but you can't draw the whole thing because there's not enough dimensions on your sheet to draw on that can represent it. Similarly, if we scale each dimension up by 1, we've got 2 dimensions to draw on now, but now we need to put on, like, show something 4, and that cannot be done. But we can do representations. And there are different ways to represent 4-dimensional things. So one way is projections. So imagine I have a cube over here, and I have a light, and I shine a light at the cube, and it's one of those cubes that just has the edges showing, so you can, like, see through it and stuff. And we would get a pattern that looks kind of like this. We'd have a little square here, 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 here. So like 2 squares, a little one and a big one, and their vertices would be connected. And you'd understand that as a 2-dimensional projection of a cube. What if we have a 4-dimensional cube, just like that? That's called a tesseract. I'll get more into that later. And we have it above our hyperplane, and we shine a light onto it. And we'll have, instead of a 2D projection, we'll have a 3D projection. And that I can show you, and I've got one right here. So this is a projection of a 4-dimensional object. Notice that the object itself is 3-dimensional. It has length, width, and depth. But the object it represents is 4-dimensional. So that's one way of representing 4D objects, through projections. But we do lose some detail. Just like when I projected the cube onto here, when you have a cube, each vertices has 3 right angles. They all look like this, right angles, all of them, and they're connected into a cube, right? But here, there was only a right angle. Some of them have right angles, but each vertice has one edge that is not right angled to the other 2. And that's a problem. But this thing is similar. Like the actual tesseract, each edge, there would be 4 edges for each vertices, and they would all be perpendicular to each other. Right. Oh, okay. But this thing, if you look closely at it, well, 3 of the edges on each vertices are perpendicular, but there's a 4th one that isn't. And that's just the cost of losing a dimension, because we lose accuracy. But we can still kind of grasp the concept. Okay, so what if you want a way to see 4-dimensional objects? You want to see them more accurately, but of course to do this you can't see them very